I named this presentation differential pair, but in terms of network theory, we don't like this new word. We don't like to introduce all kind of different, let's say, words, because if we say anti-series connection, we immediately know the properties of the connection, because we have seen anti-series connection of two identical devices will result in odd characteristic. I don't need any other knowledge for that, because that is what we have discussed before. So that's why the anti-series connection is a very nice name. So the anti-series connected CS stage is what we are going to do now. So this is what we had. We had two nonlinear two ports, and we want to connect them anti-series. And if they are exactly the same, we might as well do this, because then there is no voltage difference between the two minus inputs and the two minus outputs, because the elements are exactly the same. And then placing the MOS in it would just result in a differential pair as we would have it. You can also put two vacuum tubes in it, or two biased NPN or PNP devices, bipolar transistors. Any three-terminal element will do. So that's why it's nice to speak about this method, because now we know that the modifications that will happen to the stage are valid for all kinds of stages that can be generated with anti-series connection. If we bias the common source stage, then we have seen we need 4 bias sources, and then we connect them together. That would give us 8 bias sources. So here they are. We have the 4 bias sources as we have discussed in the previous lecture, and put them around each device. And now you see at the output that VDS, for example, these two cancel each other. You know, they have plus minus and minus plus in series, so they canceled. And at the input, VGS also, they cancel each other. If you would look differentially at the input, you don't see them. So we could bias this stage as done in with the two terminal elements with current sources only. That's the next step. But first I want to tell you something extra. Apart from having a odd characteristic created, so we have no offset. Cancellation of offset is obvious because it's a zero order term, and that's an even term, and even terms cancel if the devices are let's say equal. And of course, because the matching is not perfect, there will remain some residual offset, but in the concept we cancel the offset and we cancel all even terms. But we have something else. We have created a 4-terminal network. Look to the upper picture. We started with 3-terminal networks in which it is hardly possible to create isolation between source and load, because source and load have to be interconnected with the common terminal of the amplifier stage, which is the source. But by placing them anti-series, we get a 4-terminal element. So we can apply this differential pair. As such, we can say, well, the reason to use a differential pair is, I see that there are some plus minus signs wrong in the second one. I will correct that on the sheet. But the reason that we can use a differential pair is that we can create or improve port isolation in amplifiers. You could say we have a plus input and a minus input, and now we also have a plus output and a minus output, and by flipping them we can make either an inverting stage or a non-inverting stage. So that's the degree of freedom that we get from the differential pair. So we have a 4-terminal stage with improved port isolation. That can be very useful for us later on in the design of amplifiers. And this is the way of design of biasing the whole thing with current sources, because you see all the voltage sources cancel. You don't see them. Of course, we measure them as common mode voltages. That will be on the next page. But as you see now, I have 5 current sources, and the sum of all these currents should be 0. And the voltage of the device in this way is not at all defined. So we need external circuitry to define at least the voltage at one node, and then the rest will be defined by the the common mode voltage at one port, sorry, and the other voltage will then be defined by the device characteristics. Common mode biasing will be an issue that we will discuss later. So this is not, let's say, happening automatically. We have to do something about it, but now you are aware of the fact that the whole thing is somehow, uh, let's say, the potential with respect to ground is not defined, and we have to define it. So common mode voltage at one port has to be defined by the application, and then the other port follows from the common mode bias sources and the device characteristic. So let's go to the VI transfer, and we only do voltage to current here. In this case, you know, the transistor behaves more or less like a voltage controlled current source. We could also do all the other transfers, but let's say we only focus on this one for the moment, and all characteristics that you can imagine will of course become odd. Offsets will cancel. So here is a circuit that I use for LT-SPICE to generate the differential input voltage between the gate G1 and G2. So I only, my signal voltage is V3, and I copy this one anti-series with this -1 gain in E1. So if G1 goes up, then G2 goes down. And if there is no signal, then it's exactly in the quiescent operating point. And I bias the input at 0.9 volt, halfway the power supply, and I just tie the drains to 1.8 volt, the full power supply, and measure the two current. So the condition under which this differential pair is driven is that the common mode input voltage is kept constant, 0.9 volts. See, V1 is setting this common mode input voltage, and the gate 1 is lifted up and the gate 2 is pushed down with the same amount, or the other way around. This is of course not a condition that it is always used in a circuit, but this is the test condition that is applied here. And with this test condition, we can clearly illustrate the behavior of this stage. So the common mode voltages are basically fixed by V1 and V2. At the input V1, 0.9 volt, and at the output, the power supply. And then you here see a plot, and the currents in the legend are not on in the right order. You see first 100 nano, then you see 100 micro, and then 10 micro, 20 micro, 50 micro. That is how the program did it, and I didn't sort it. So be aware that that is the case. And what you see is the relative output current. So it is the output current ID1 minus ID2, the differential output current, divided by I1, what we call the tail current ISS. So I am changing the operating point current all the time and plotting the ratio of the differential output current and the operating current. That shows you that when the device is operating, let's say the red one is 100 nanoamps, when the device is operating in weak inversion, that it just behaves like a bipolar differential pair. We have about 50 millivolt for a linear input range, and then we have the full excursion. Of course, the full excursion is only plus or minus 100 nanoamps. If you go to the blue one, which is 100 microamp tail current, then the device is more operating in the strong inversion, and you see it becomes almost completely linear. Well, of course, it depends on the way of zooming it. There will be, of course, a derivative that is non-zero, but you see that the range now is much wider. It needs a wider voltage range, of course, and the all terms, of course, are gone in every transition, and the device is more linear. So odd characteristic and increasing linearity with the inversion coefficient. That is important to know. But it is a linearity of the voltage to current transfer. And that is not always the relevant transfer. We have 4 transfers in a transistor. We have voltage to current, voltage to voltage, current to current, and current to voltage. And all 4 somehow contribute in a circuit to the nonlinearity. Let's look at this SS node, the connection node of the 2 sources. And you see that when the transistor is operating, is in the range that the current is flipping from one transistor to the other, so it's not yet saturated, it's not delivering the full output current, then the voltage, the common mode input voltage, does not change. But if the voltage becomes larger and the device is either one device is fully conducting and one device is fully off, then you see the even characteristic of this thing. And then you can really see it, of course, in the red one. And you could call this a rectifier. It's a even function. So the common mode voltage here is an even function, while the differential mode quantities are odd, the common mode quantities are even. That's important to know. That happens in balanced circuits. So even characteristic we have here. Let's go to the small signal transfer. And let's first look, before we are going to study the differential pair in detail, what we have to study, because maybe we can already predict on a much higher level what is going to happen if we are connecting two ports to each other. And in this case, use an anti-series connection. So here you see, I have two ports, and we have characterized them with our transmission one parameters A, B, C, D, and we assume that both 2 ports are completely equal. So then you could calculate the resulting ABCD of the total structure of the dashed 2 port, and then you see that nothing happens with A and D, but B is 2 times larger and C is 2 times smaller. That is the result of series connection. And of course, if we have linearized the whole thing, so we're talking about small signal behavior, so we have linearized the whole thing, there's no difference between series connection and anti-series connection. So the small signal diagram of the differential pair, we can just use these conclusions now, and this would be the small signal anti-series connection of the 2 differential pairs, one having the elements with 1 subscript and the other with 2 as subscript. And if they are both operating in the quiescent operating point, so, and they are completely equal, the devices, we can simplify this to this structure. I didn't plot here an output capacitance. Of course, there is a source, a drain to bulk capacitance at both transistors, and that adds up to a output capacitance. You can just add it to the circuit. So here you have the equivalent model of the in the quiescent operating point, and you see GM gets half the value of the element of one of the constituting elements. The CGS has half the value. It's the series connection of 2 capacitors. CGD is still the same, and RO is 2 times larger, so GO is half the value. So CGS, CGD, GM, and RO are the small signal parameters of the constituting CS stage. That's what you should know. So then what remains is the noise. We have discussed the large signal behavior. We now have seen the small signal behavior, and so we can the small signal dynamic behavior, and that we know, now that we know the small signal dynamic behavior, and we know ABCD of the total construction, the total structure, then we can talk about the noise. So let's see the differential pair stationary noise. So let's also look at behavioral modifications resulting from anti-series connection of linear two ports, because then we can maybe do the whole noise analysis much easier than if we completely plot all the noises of the transistors in it. So let's see. This is two ports connected anti-series with their noise sources. Of course, the noise sources are here uncorrelated. Although the two ports might be identical, their noise will not be correlated because it is different things, and the different things have different noise. Now, maybe you would like to transform this IN1 and IN2 by splitting them somehow and getting them to an input, because what we want is we want one current noise source between the input terminals. And now we have two current noise sources to this common terminal here, this minus inputs. And splitting is not going to work. You cannot get rid of it. In fact, we used a not very handy representation of the noise sources for finding the total equivalent input noise. Because you see already at the input, VN1 and VN2 are just in series. So if we would use a model having output voltage noise sources and input voltage noise sources, then we can add them at the output, giving us one voltage source at the output, because it's just at the output, it's series with the output port, and then we can use the transmission one parameters of the total construction to find a input equivalent. So we have to convert this noise model into something that is more convenient for this operation. And that is done here. We can, and this is, the example is done in the book. There you will find the derivation of all these sources. So we can replace IN1 with two correlated sources at the input of voltage sources, one at the input and one at the output. At the input, we can add all the voltage sources or the spectra if they are uncorrelated. And at the output, we can add them, and we can convert the output voltage source, of course, back to the input using, well, we have voltage source here, so we need to multiply it with C or with A. That's what we need to do. With A, it would give us a voltage source, and with C, it would give us a current source. And if you do so, you will find this result, because we are now using A, 2B, C over 2, and D of the complete structure of the two ports to find the input. And this is the result. Again, you can find the derivation of this in the textbook. So the result is that we have SV, the total, the spectrum of the input noise voltage, as the sum of the two spectra of the individual two ports. And we have SI as, well, it is half the current, but the spectrum is squared. So it is 1/4 times the sum of the two spectra. So you can see if both values of the spectra are equal, you end up with double voltage spectrum and half the current spectrum. So conclusion, the equivalent input noise sources of a differential pair equal those of the CS stage if, well, you see they don't equal. Here the voltage is 2 times larger and the current is 2 times smaller. So what if we are going to make those voltage sources smaller by using wider transistors and increase the current? If we do so, we make each transistor in the differential pair 2 times wider than the CS stage that we want to compare with, and we make the current in each transistor 2 times larger, then we end up with exactly the same noise sources, which gives the conclusion that we have the same performance for 4 times more area and 4 times more current. And you see, this is the beauty of finding those conclusions on a higher hierarchical level. We don't need to dive into the details and study all the noise of the CS stage and the differential pair separately. No, we just know what is the result of a what is the behavioral modification resulting from anti-series or a series connection of two equal two-ports. So there's a SLICAP model for the differential pair. And the symbol in LT-SPICE is SL, SLICAP, X for subcircuit, MD for MOSFET differential. So this is the symbol. And the parameters that you can give to this thing are the width, the length, and the drain current of the constituting transistors. So not of the total differential pair, but of the constituting transistors. That's what you do. And then the question mark, you can put in the name of your subcircuit. And the name of the subcircuit that accepts these parameters is CMOS 18N differential and CMOS 18PD differential. So this is for P devices, the latter one, and the first one, of course, for N devices. And the small signal model is as discussed before. And this comes from the manual of SLICAP, so you can find it in the manual as well. Later on, when we are going to talk about negative feedback and put stages in an amplifier, and we want to calculate the loop gain, we need a reference variable, a control source to select as reference for the loop gain. And if we have a differential pair with two control sources, then you can never take the differential pair as a whole as one stage. And that is why we introduced this model in SLICAP. You see, there is now only one control source in the device. Assuming, of course, that both transistors operate at the same operating point. So this is the story about the differential pair.